Okay, let's look at exponential growth and decay. Exponential growth or decay happens when an amount of something increases or decreases by a constant ratio or percentage at every time increment. Examples of exponential decay or growth and decay is our compound interest. So we have a sum of money, and then that if we're investing, that money gets increased every year at a constant percentage of say 4%. And it's that constant ratio or percentage which makes it exponential. If it's not a constant ratio, then it won't be an exponential growth or decay. So compound interest is a classic example of exponential growth. If you're investing money, your amount of money increases every year by a constant percentage. Other types of exponential growth and decay that we can see in nature is population growth. If you're looking at how cells divide and multiply themselves, they double every single time period. So our ratio, it's doubling. Also, if you're looking at radioactive decay of atoms or elements, that can also be modeled using exponential growth or decay. Now, what's the magic formula for exponential growth or decay? An exponential function or formula looks like a equals a naught, so a with a little zero at the bottom, multiplied by some growth rate b to the power of time. So a is your amount, so it could be your amount of money, or it could be your population, the number of cells, etc. A naught is your initial amount. So when time is 0. So when you start investing money, how much did you put in the first place? So that's your initial amount. Your B is your growth or your decay rate. And again, it has to be a constant ratio or rate for it to be an exponential growth or decay. If it's not constant, it can't be exponential anymore. And t, the power of t, so that's time. So if your rate or your base is bigger than 1, then it's a growth, exponential growth. And if your base is a value between 0 and 1, then it's a decay. So you're decreasing the amount that you have. So let's look at a few examples to see how this formula works out. So example 1, determine a rule for the following scenarios. So scenario 1, John has a painting that is valued at $100,000 and is expected to increase in value by 14% per annum. So we need to create a model of this situation. So John has a painting that is valued at $100,000, and that amount is expected to increase by 14% every year. So when we start doing these formulas, we first need to define some variables. So what we're interested in is the value of the painting. So let's define our variable. So let A equal the value of the painting, because we're trying to look at how does the value of the painting change. So let A equal value of painting. What's the units? It's in dollars. And our other variable is time. So let T equal time, which is in years because it's per annum, per year. So let's draw up a table to see how the value of the painting changes per year, and then we can need to establish that the ratio between the paintings every year is a constant ratio before we can establish that it's an exponential growth or decay. So let's draw up a table. So at the top we have time, we have the amount of painting, of the value of the painting, and then the ratio. Let's do a few years. So when time is 0, how much does the painting cost? So we're told that when time is 0, the painting costs $100,000. So when t is 0, A is 100,000. When t is 1 year later, how much is the painting worth? Well, it says the painting increases in value by 14% every year. So after 1 year, we would say that it's the original amount, which is 100,000. In addition to, because it's an increase in value, we're adding on 14% of the original amount that we had last year, which is 100,000. So 100,000 plus 0.14 times. So 100,000 plus 0.14 times 100,000 gives us 114,000. Well, let's work out the cost of the next year. So in year 2, we have, what's the cost for the painting? Well, it's the cost from the previous years, which is 114,000, increased by 14%. So plus 14% of the value of last year, which is 114,000. So that's the same as 114,000 plus 0.14 lots of that amount. So using a calculator, we get 129,960 $129,960. Let's do it again for year 3. So the cost of the painting after 3 years is whatever it was worth last year, which is 129,960, increased by, so adding 14%. So it's 14% of the value from last year. So putting it into a calculator means we get 259,920.14. So just highlighting, at time 0, our value of the painting is $100,000. After the first year, we calculate a 14% increase, so it's $114,000. After 1 more year, let's increase yet another 14% of the previous year's amount, so we get 129,000, etc. And in the 3rd year, we get this amount after an increase of 14%. So then let's look at the ratio. Ratio means we divide. So the first ratio is dividing the price of year 1 over the initial price. So in other words, it's 114,000 divided by 100,000. Using a calculator, you get 1.14. The next ratio is dividing the second year amount by the first year's amount, which is 129,960 divided by 114,000. So that's 1.14 as well. Well, that's a good sign because we ultimately want our ratios to be the same or to be constant. So let's look at the last ratio, or the next ratio, and see if it is constant. So year 3 amount divided by year 2 amount, which we get using a calculator, we get 1.14. Well, that's very reassuring because, as we said before, the ratios, we want it to be a constant ratio, otherwise we can't use an exponential growth. So all this table calculation work is just to help us establish that it is a constant ratio, and hence we can use an exponential model as a result of this constant ratio observation. So, etc. So we can say that the ratio appears to be constant of 1.14. Therefore, we can use an exponential model. Well, what's the default formula for exponential model? It was A equals A naught times B to the T. So A is one of our variables, the cost or the amount of the painting. A naught is the initial amount. So when time was 0, how much was the painting? Well, 100,000. So our A naught is 100,000 multiplied by the base, so B. Well, what is that constant ratio that we calculated? 1.14. So B is 1.14 to the power of T, because T's our other variable, the time in years. So therefore, A equals 100,000 times 1.14 to the T. That is our model for this scenario. A subsequent question could be, well, what is the value of the painting in 20 years' time? So you can make predictions based on this model. So rather than having to do this horrendous table calculation of year after year after year, we can literally just put T equals 20 into the formula and work it out. So the question could be, what is the value of the painting after 20 years? So essentially you're trying to calculate, when T equals 20, what is your final amount? So using the formula from above, 100,000 times 1.14 to the power of 20, using a calculator, you get 1374348.99. So therefore the painting is worth approximately $1374349 in 20 years time. So again, you have to establish it's a constant ratio of values before you can apply the exponential model of the A equals A naught times B to the T. Let's do one more just to make sure we're okay. So again, we're trying to determine a rule for the following scenario, and the scenario is a city's initial population of 50,000 is decreasing by 12% per year. So it's a word problem. Let's start off by defining our variables. Well, what are we trying to find? What are we trying to model? So let A equal, well, we're looking at the city's population. So city's population. So let A equal the population of city. In other words, we're counting by number of people. And the other variable, it's typically time. T for time. What time increment are we going up in? It says 12% per year, so our time is in years. Before we can jump in and just plug in an exponential model, because we know this is from the exponential chapter, we actually first have to draw up a table and establish, again, constant ratio before we can plug into our exponential model. Feels like a lot of work, but it is good communication to establish why you can use an exponential model first up. So draw up a table. From the last example, we might need to draw up a bigger table space because we ran out of space before. So T, A, and a ratio. Right, when time is 0, what is your initial population? The question tells us it is 50,000. After 1 year, what is the population of the city? Well, it says there it's decreasing by 12% every year. So year 1 is what we had last year. We're decreasing, so we're subtracting 12% of whatever we had last year. So it's 50,000 minus 0.12 times 50,000. If you grab a calculator, that gets you 44,000. Let's do it again for year 2. Let's see how much we have left in terms of people in the city. So the amount we have left is 44,000 minus 12% of the amount we had last year, which is 44,000. So using a calculator, that's 0.12 lots of 44,000. We get 38720. We'll just do one more just for good measure. We're taking away 12% of what we had last year because it's a decrease of 12% every year. So using a calculator, we get 34073.6. Now let's look at the ratio. Remember, ratio, we're dividing 1 year's population of the other, so A1 over A0. So we have 44,000 divided by 50,000, which gets us 0.88. Let's calculate the second ratio. So A2 divided by A1. We get 38720 over 44,000. Using a calculator, 0.88. Let's do one more for good measure, just to double check it's a constant ratio. And look, using a calculator, thank goodness we do have a constant ratio. Because it's a constant ratio, we've established that, we can say that yes, we can apply the exponential model. So ratio appears to be constant of 0.88. So therefore we can use an exponential model. So what's the generic exponential model? Remember, A equals A0 times B to the T. So quote your default one. A equals A0 times B to the T. So A0, how many people were in the city at time 0? At time 0 we had 50,000 in the city. So A equals 50,000 times B. B is your constant ratio. Your ratio is 0.88. So times 0.88 to the power of T. So that is your model. Again, we can also work out a subsequent question of how many people are there in the city after 10 years. So how many people are in the city after 10 years? Well, essentially we're asking when t is 10, what is the amount of people you have in the city? So A equals 50,000 times 0.88 to the power of 10 because t is 10. So using a calculator, we get 13925.05. That's the mathematical answer, but people can't be 0.05, can't be decimals. So let's write a sentence conclusion and write a contextual answer. So therefore, there are approximately 13925 people in the city after 10 years. So the key thing to take away from exponential models is your generic exponential model is A equals A naught times B to the t. A is the amount of interest, A naught is the initial amount when time is 0, B is your ratio or your growth or decay rate, and t is your time. So it's the power of time. Now, to be an exponential growth or decay, it has to be a constant rate or ratio. If it's not constant rate or ratio, then you can't use the magic exponential formula. And exponential, if you're wondering why do I need to memorize or learn this, it's actually used a lot in our daily lives when we're trying to model how animals or populations grow throughout time, or in fact investing in money as well. So to-do list for this section: exercise 3J. Fifteen's optional because it's very similar to 14. If you can do 14, you should be able to do 15 as well. The nice one is question 16. So they might be a little bit tricky to pick up at the beginning, but after a few tries, hopefully it'll get a bit more familiar. Alright, have fun.